All right, today we're cracking open the digital toolbox of the modern scientist. We're going to dive into the essential programming languages that power everything in computational materials science, the tools that let us design brand new alloys and simulate atomic structures right from our keyboards. So let's get into it.
So, here is a real head-scratcher for you. How do you actually test a material that hasn't even been made? I mean, this is a daily challenge for engineers and materials scientists. You can't just throw some chemicals together and hope you get the next super alloy for a jet engine. You have to know its properties before you create it. So, how on earth is that possible?
Well, the answer is you build a virtual one. That's right. Instead of beakers and furnaces, scientists write code to create these incredible digital laboratories. And inside these virtual spaces, they can simulate unbelievably complex stuff, like how heat flows through a piece of metal, or the stress on a bridge, or even how a material's microscopic structure changes over time.
But before we can meet the languages themselves, we kind of need to understand the rules of the game. What actually makes a programming language a great choice for scientific work? Turns out, there are a few key things every researcher is looking for. First off, speed. It's totally non-negotiable. We're talking about simulations that involve millions, sometimes billions of calculations, so efficiency is everything. Second, it has to be a rock star at matrix operations. That's the mathematical bedrock of this whole field. Third, you need powerful ways to visualize your data. I mean, a mountain of numbers is useless if you can't see the results, like the stress patterns or temperature fields. And finally, it's got to be extensible, so scientists can build on their tools and adapt them as their research gets more and more advanced.
Okay, so with those rules in mind, let's meet our first two contenders. Think of these as the agile, user-friendly options, the tools you grab when you want to sketch out an idea and see if it works fast. They are the prototyping powerhouses of the scientific world. First up is MATLAB, and its name literally stands for Matrix Laboratory, which tells you pretty much everything you need to know. It's a high-level language that was designed from day one for a single purpose: numerical computing.
And let me tell you, it is unbelievably good at its job. MATLAB has matrix operations baked right into its DNA. It's just packed with numerical libraries and fantastic plotting tools, all wrapped up in an interactive environment that makes it perfect for quickly trying out new algorithms and testing ideas on the fly.
And just look at the simplicity here. That single line of code, that one backslash, it solves a whole system of complex linear equations. In a lot of other languages, this would take way more code and setup. This is MATLAB's superpower in a nutshell: rapid, powerful prototyping.
Now, on the other side of the ring, we've got Python. Now, unlike MATLAB, Python isn't a specialized scientific tool by its nature. It's a general-purpose language that can do pretty much anything. It becomes a scientific beast through its absolutely incredible ecosystem of add-on libraries.
And that ecosystem, that's the real game changer here. You've got libraries like NumPy that give it powerful matrix abilities, SciPy for all sorts of advanced algorithms, and Matplotlib for great-looking visualizations. And maybe the biggest advantage of all, Python is completely free and open source, with a massive active community. This is why it plugs so perfectly into the cutting-edge worlds of data analysis and AI.
So here's that exact same problem but solved in Python. The core logic looks pretty similar, right? But notice that very first line, import NumPy. This perfectly illustrates Python's whole philosophy. You start with a super flexible base, and then you just import the specialized tools you need for whatever job you're doing.
So, to sum it up, it really comes down to this. MATLAB is the specialized tool, like a dedicated high-end workshop just for numerical analysis. Python is the versatile generalist, the language that can build a website one day and then turn around and do high-level scientific research the next. They're just two different philosophies, but both are incredibly powerful.
But okay, prototyping is one thing. What happens when your simulation is so massive it needs to run for weeks on a supercomputer? Well, that's when you call in the heavy hitters. It's time to meet the high-performance titans. First up, C++. And the keyword here is compiled. What does that mean? Well, unlike Python or MATLAB, the code gets translated directly into the computer's native machine language before you even run it. That extra step makes it blisteringly fast and gives the programmer pinpoint control over system resources, like memory.
And all that raw efficiency is why C++ is the foundation for huge, industrial-grade simulation software. You know, the kinds of programs that model car crashes or simulate how millions of individual molecules behave. But, and this is a big but, the trade-off for all that power is a much steeper learning curve and a lot more complexity. And you can totally see that complexity reflected right in the code. I mean, just squaring a number looks a lot more formal, doesn't it? You have to declare variable types, you've got this rigid syntax, but it's precisely that structure that unlocks its incredible speed.
And now let's talk about a true living legend, Fortran. Its name actually stands for Formula Translation, and as one of the oldest programming languages still in use today, it remains an absolute champion of raw numerical speed.
So you might be asking, a language from the 1950s? Why are we still using it? Simple, because it is ridiculously good at one thing: pure, unadulterated number crunching, especially when you're dealing with massive arrays of data. Decades and decades of work have gone into optimizing its compilers, making it this irreplaceable cornerstone for critical fields like climate modeling and fluid dynamics.
And when you look at the code, you can just feel its scientific DNA. The syntax is so straightforward, it almost looks like you're just writing out mathematical notation. It was designed for scientists who need to translate complex formulas into fast, efficient code without any extra fluff getting in the way.
All right, we've seen the agile prototypers, and we've seen the high-performance titans. So, which one wins? What's the right language for a scientist to pick? Let's bring them all together for the final verdict.
As you can see, each language has its own turf. MATLAB is the king of quick algorithm development. Python is the star when it comes to data analysis and plugging into the world of machine learning. C++ is what you choose when you're building massive, high-performance simulation codes. And Fortran? It's still the undisputed champ for pure, efficient computation in some of the most established scientific fields. And that right there brings us to the single most important takeaway of this whole explainer. The answer isn't about choosing one language to rule them all. That's not how it works. Modern scientific computing is what they call polyglot, meaning it uses multiple languages. A common workflow might be using Python to clean up some data, feeding it into a core simulation built in C++ for maximum speed, and then using Python or MATLAB again to visualize the final results.
And when we talk about the most demanding simulations, the really huge ones, they're all happening in one place, the arena of high-performance computing, or HPC. On these massive supercomputers, the raw efficiency you get from compiled languages like C++ and Fortran isn't just a nice-to-have, it's an absolute necessity.
So all of this leaves us with one last big question for the future. As artificial intelligence and data science keep merging with traditional simulation, this whole landscape is shifting. Will Python's amazing flexibility and AI integration make it the dominant force? Will the never-ending need for raw speed keep C++ Fortran at the top of the pyramid? Or is there an entirely new language out there, just waiting in the wings to become the next essential tool for scientific discovery?